In a previous chapter, when we talked about derivatives, we started our discussion with the idea of derivative, and then we took the derivative of a number of polynomial functions and some of its close cousins. But then we needed new techniques to deal with situations like composite functions, and we introduced the chain rule to deal with that. Now, with integration, it's a similar kind of thing. We can integrate functions that are polynomial functions, and again, some of its close cousins, but it's a different matter to deal with something like composite functions. Now, the chain rule can help us understand what is going on, and we're going to look at two distinct kind of techniques here. With the simpler composite function structure, we can just look at pattern recognition, and that's what we're going to do at first. Remember that the chain rule now is this, that the derivative of f of g of x, a composite function structure, is f prime in terms of g of x times the derivative of the g function. And another way to look at it using the u notation is like this. If we have y is f of an expression u, plus some constant c, and I'm throwing the constant in here because we're going to work this backwards, but usually we wouldn't even see the c part of this when we were using the chain rule. I'm just emphasizing that if a constant is in here, it could be, and it would be fine, and here's what we would get for the derivative. The constant would go out, you see. So the derivative of y prime, is f prime in terms of u times the u prime. And this is perhaps the simplest way to look at the application of the chain rule. Now with integration, we're going to work this in reverse, and all we need to do is recognize the pattern that we have here in order to move to this kind of structure. Now when we have this notation of the prime when we talk about derivative, and we have a different notation when we go in the other direction. When we talk integral, we talk about the integral function as a function designated with an uppercase f. So if we think in terms of this derivative function, this f prime of u, as just being a function of u, then the integral function, this function that we would have started with, would have been big F of u. So we can think of this then in terms of integration. If we integrate this, then we get that. I think an example goes a long way to tell us how this situation is working. Here's an example of a specific problem, and we're going to take it from the very top. That is, we're going to differentiate first. We're going to use the chain rule, and then we're going to use the chain rule sort of in reverse in order to integrate. So it looks like this. So we have y is 1/5 x squared plus 1 to the 5th plus 3. Now if we were differentiating this, if we want the derivative of this, then we would recognize the situation as an inner function, an outer function, you see, and with that kind of structure we implement the chain rule. And the chain rule says to take the derivative of this, now this just goes out, it's just clutter, so the constant will go out, but take the derivative of this in terms of this single entity. So the 5 times 1/5 raised to a power 1 less than that, and then you multiply that times the derivative of the single entity. So we have 1/5 times 5 times single entity to the 4th times the derivative of this is 2x. And now it's a matter of cleaning up. The 1/5 times 5 is 1, and we just bring these things down. Now, now we're going to go in the other direction. We're going to say, well, let's say we have this and we want to move up here. And it's just a matter of recognizing that we have an inner function, an outer function, and we have the derivative of the inner function. That's an important property in this recognition process. So it's inner function, outer function, and derivative of the inner function. And once we have that, we can take the integral of that rascal, and it turns out to be the integral function of this outer structure plus a constant, and that's it. So it's x squared plus 1 raised to 1 power greater than this over that same exponent. And then 1/5, this can be expressed as 1/5 x squared plus 1 to the 5th plus c. Now, notice the plus c here is tacked on. Look at this and look way up here at what we started with, it's the same thing. We had a specific constant here, and when we integrate back, we're getting a general constant, and that's the only difference in these two expressions. Well, here's another way to look at it. It's the same idea, just another notation or a variation on the same notation. We have the inner function g of x. The outer function is this raising to the fourth power, and we have the derivative of the inner function. And when we have that structure, we can take the integral of that structure, and the way we integrate is to take the antiderivative of this, and we get that. Okay, antidifferentiation then of a composite function. And again, here's the same structure once again right here. We're integrating f of g of x times g prime of x. Here's the structure we're recognizing. When we recognize it, it's the integral function of the g of x, and then plus a constant. Now, before I go into the next part on the board, I mentioned to you that there are a couple of techniques that we're going to look at. One of them is pattern recognition, and that's pretty neat as long as we can, we want to be able to recognize the pattern, but sometimes the pattern doesn't exactly fit, and so we have to use some varying techniques. And the techniques will be the substitution of a variable, and that variable substitution will involve the u. And to get us ready for that, I want to show you this in terms of the substitution idea, or in terms of the u notation, just so that we can get familiar with that notation. You see, the u can stand in for g of x. And this part, the g prime of x dx, can be du, you see. So it's f of u du, so we're integrating this. The du now is the g prime of x dx, and we get, once we have this, then the antiderivative is the antiderivative function of the u plus a constant. All right, the pattern, the situation can go very, very rapidly once we see the pattern, and we can see it very, very quickly. Here, for example, in integrating this, where we look at the structure like this. We have this inner function. It's raised to the third power. We don't care what that exponent is. It's this inner function that we're really concentrating on, and whether or not that part is the derivative of this part, you see, and it is. So, and the derivative here would be negative 4x, so we do indeed have the pattern that we're looking for. So to integrate, we're integrating this, you see, in terms of that single entity. So it's this single entity raised to 1 power greater over that same exponent, and then plus a constant, and clean it up a little bit, and it looks like this. Now, a lot of times we can check these rather easily by performing the inverse operation. That is just by differentiating. So if we want to check this situation, we're starting out with y equals this, and then y prime then is, well, let's see, using the chain rule, it would be 4 times 1/4 times the single entity to an exponent 1 less than that, times the derivative of the interior, which is the negative 4x. Cleaning it up, then we have y prime is this, and this is exactly what we started with. So we have verified that the integration was done correctly. Here's a problem involving a trig function. We're integrating 5 cosine 5x dx, and notice that we're meeting the pattern here. The inner function is 5x. The outer function is cosine. The cosine idea. The inner function is 5x. The derivative of 5x is 5. Now notice the derivative is out here, and we're a little more accustomed to seeing the derivative part on the other side. So we could rewrite like this to see it maybe a little more clearly. But we go through that process of integration. Once we recognize the pattern, we say, gee, we just want the antiderivative function of cosine 5x. You see, and it's sine 5x plus a constant. We can check it by thinking of this as an original function and then taking its derivative. The derivative of sine 5x is cosine 5x times the derivative of 5x, which is 5. Sometimes the pattern is not exactly right for us. We're missing a constant, and the constant multiple rule can help us deal with that situation to make the pattern occur. Remember, the constant multiple rule is the integral of k times f of x is k times the integral of f of x. We can kind of extract a factor if we want to. So it allows us to build in constant factors in situations such as this one. Now, once again, notice that the candidate for derivative portion is on the left of the portion in parentheses. And we ought to be able to recognize it either way. We can write it over on the other side and it would be fine, but we ought to be able to recognize it either way. What we should recognize here, though, is that x is not the derivative of 4x squared plus 3. The derivative of 4x squared plus 3 would be 8x. So we're missing an 8 factor here. But we can multiply it into the problem by multiplying in 1/8 times 8. So we're multiplying by a factor of 1, which doesn't change the value of what we're integrating. And the 1/8 part we can express outside of the integral notation, and the 8x we express inside to fit the pattern. So now that we have the pattern, we can integrate by taking the antiderivative function of this single entity to the third power, and it's single entity to the fourth power over 4 plus c. And then it's a matter of cleaning up. The 1/8, the 4 comes out and joins the 8 here in the denominator, so 1 over 32 times the binomial to the fourth power plus c. Now, let's use this same problem. It's important to use the constant multiple rule, yes, but it's also going to be important for us when the problems get a little more complicated than this, for us to be able to use some substitution. And I want to show you how the substitution idea works on a simple problem like this that we could work in another way. So the substitution idea works like this. Here's our problem. Now notice I've written the x factor on the right side just as a convenience here. It is, when we start this substitution process, that is kind of helpful to us to have the x, the outside part, the candidate for derivative part, next to the dx, and you'll see why in a minute. But suppose we let u stand for this inner function, this 4x squared plus 3. Then du, the derivative of this, would be 8x dx. 8x dx. Now, if du is 8x dx, but what we have up here is x dx, then we can solve this for that, you see, for the x dx part. And we can do that by dividing on both sides by 8. So du over 8 is the x dx. So when we make the substitution, it comes out rather clean. It is that u is being substituted for the 4x squared plus 3, so we have u cubed. And the x dx, we're substituting du over 8 for that. So here we have our problem. Now, this is a little bit simpler than using the more complicated binomial involved in the problem, but it allows us now to extract the 8 as 1/8 outside of the integral notation, and now we integrate u cubed du, and it's u to the fourth over 4 plus a constant, and we're multiplying, notice, times the 1/8. And then we extract the 4 over here to make this 1 over 32, and do the back substitution for the u, giving us back our binomial to the fourth power plus c, which is what we had before. Now, this method is not particularly any more efficient than the previous method. I think the previous method was perhaps even more efficient than this is. However, this method helps a great deal in a problem such as this one. It's the integral of x times the square root of 2x minus 1 dx. And it looks like we're not even close to the pattern that we're looking for. I mean, if we think of 2x minus 1 as the inner function, then the derivative of that inner function would be 2. But here we have an x. How are we going to possibly deal with that? Well, let's begin with some substitution and just kind of follow our nose through the problem. Look at what happens. This is really a neat turn of events in problems like this. We just let u stand in for the 2x minus 1. And then, as a natural consequence of this, du is, well, it's 2. You see, 2 dx. All right, well, we have a couple of things to deal with. We have to find some kind of substitution for x. We have a substitution for the 2x minus 1, and it'll be u that substitutes in there. We can solve this for dx to have a substitution for dx. We saw that kind of manipulation before. We can just say this is du over 2, and that'll be the substitute for dx. All right, that's pretty easy. We need to write x, though, in terms of u. Oh, we can do that by manipulating here. So we just solve this for x. And to solve this for x, we'll add 1 on both sides and divide by 2. So this is u plus 1 over 2 is our substitute for x. So we have 3 things that we're using out of this grouping right here. And here's how the substitution goes. It's the integral of, now let's see, x. Well, x is the u plus 1 over 2. And let's see, this is u, the square root of u. You see, so it's u to the 1/2. And then the dx is du over 2. Oh, how nice. Now everything is in terms of u, and that's what we wanted to accomplish. Take out all the x's and write everything in terms of u. And so now let's manipulate and clean up a little bit. These two denominators can come out as 1/4. And the u to the 1/2 multiplies times this binomial. U to the 1/2 times u is u to the 3/2. And then u to the 1/2 times 1 is u to the 1/2. And then times du. Oh, how nice. We can deal with this rather directly, almost like a polynomial function, or one of its cousins. At any rate, it's 1/4 then times the integral of this is, let's see, to integrate here, it's u to the 5/2 over 5/2, and then u to the 3/2 over 3/2, and then plus c. And that's all there is to it. Now, it's a matter of cleaning up and back substitution. This is, this 5/2 in the denominator becomes 2/5. So this is 1/4 times 2/5 u to the 5/2 plus 2/3 u to the 3/2. I've written that up here, and I've gone ahead with the rest of the problem. But it's 1/4, 2/5 times u to the 5/2 plus 2/3 u to the 3/2 plus c, and then 1/4 times the 2/5 is 1/10. 1/4 times 2/3 is 1/6. And then back substitute. Now notice here that in the manipulation process I have cleaned up the whole matter, the whole business in terms of u. That is, I've done all of the algebraic manipulation in terms of u before I do the back substitution. That helps to keep things less cluttered, I think, in the whole process. But at any rate, it's all cleaned up here in terms of u, and now I can just pop in the back substitution of 2x minus 1 for u in both places, and we're done. Here's another problem involving trig functions. Sine squared 3x times cosine 3x dx. And remember that sine squared 3x can be written as sine 3x squared and then times the rest of the problem. But writing it like this allows us to make the substitution here for sine 3x. So we're going to let u stand in for sine 3x. Then du, the derivative of this, is cosine 3x times the derivative of the 3x. So it's cosine 3x times 3 dx. Now, at this point, when we get to this point with the du business, we look back into the problem and we see what we're back substituting for, or what we want to substitute for. And it is, we want to substitute something for cosine 3x dx, but we don't have cosine 3x dx. We have cosine 3x times 3 dx. So we need to divide on both sides of this equation by 3. So du over 3 is the substitute for this part of it. Now we can make the substitution rather easily. U stands in for the sine 3x, so we have u squared, and then this part of it becomes du over 3. And notice how simple this is. This is the great advantage of making this substitution, is the simplification here, and then we go back to the complication when we back substitute later. But here it's pretty easy to deal with this. We yank out this 3 in the denominator, making it 1/3 outside of the integral notation, and then u squared du becomes u cubed over 3 plus c. And so now 1/3, gee, we can snag this 3 out. This becomes 1/9 u cubed plus c, 1/9 u cubed plus c. And the u, now we're substituting back in. U, recall, was sine 3x, so it's sine 3x all cubed, or sine cubed 3x plus c. Now the situation with an inner function being raised to some exponent occurs so often in this situation that we can even establish a general power rule for integration. And that general power rule looks like this. This is just a variation on the same theme we've been talking about all along. We have used this general power rule in specific cases so many times that this is rather obvious, but it's this g function, this sort of inner function raised to some exponent, and here's the derivative of that inner function. This is the pattern we're looking for. And when we integrate, we get the antiderivative function of gx, so it's gx to the n plus 1 over n plus 1 plus c. And alternatively, with using the u notation, it's the integral of u to the n du is u to the n plus 1 over n plus 1 plus c. Okay. And using it, we can usually use it rather rapidly. I'm going to show you a couple more problems here, and we're going to march through them, and we're going to see through the substitution rather easily. I think if we have this situation, we notice that the 3 is the derivative of the 3x, and so we have the pattern that we need, and we could go right from this step to the answer if we want to. But let me massage it a little bit and make this so abundantly clear that, well, I should say redundantly clear perhaps, but just swap these two, and then it's in the form of the u to the 4th du, you see, and this is the form where we can use that general power rule. This is u to the 5th over 5 plus c, and we can do the back substitution here to put us back into the format with the binomial. And we could massage this even further, writing the 1/5 over here as an outside factor, but I think the point is rather clear. Now, it is possible here just to go from the original step down to here, if we can see through it rather easily, and feel free to do that if you want to. But I'm just emphasizing the idea of using that u notation in a problem like this. And sometimes, as we saw earlier, it's useful, very useful and needed to make that substitution. Other times it's really not important to use it at all. Here's another one. We have the integral of 3x squared times the square root of x cubed minus 2. Now, notice this part, our inner function is x cubed minus 2. And the exponent on x cubed minus 2 is 1/2. And I suggest that we burn a step to write that. Even if we're trying to do these rather quickly without using the u notation, it's, I think, important to write this as x cubed minus 2 to the 1/2 power. And now we bring this down. Notice I brought it down on the other side to kind of make it look like this g of x to some exponent times g prime of x form. But at any rate, we can go directly into the antiderivative idea here. Antiderivative of this is inner or single entity to 1 plus 1/2, that's 3/2 over 3/2 plus c. And again, we could clean it up a little bit, but this is the essence of it. Here's another one, and again here I want to show you a quick manipulation to get us into the form right quick to perform the integration. This binomial in the denominator, we want to just shift it to the numerator, so we would write this as 1 minus 2x squared to the negative 2 power, and then the negative 4x as the other factor. And then we just want to check to make sure that negative 4x is the derivative of this, and it is indeed, and therefore we're in the pattern that we want to, so we take the antiderivative function of this single entity to the negative 2 power. So it's the single entity to the negative 1 over negative 1, and again we could clean it up a little bit, and also the plus c is tacked on. Here's an interesting situation. It's x squared plus 1 squared dx. Now we would like to integrate here, and we might begin our thought process here by thinking, well, okay, let's make the substitution and see if we can follow our nose through it and see if some good things happen. We'll let u stand for the x squared plus 1. Now du then, the derivative of this would be 2x dx. Now if we're going to try to solve this for dx, we would have du over 2x is dx. Gee, that doesn't help us very much. If we substitute this back into here, or when we write the next step, we still have an x involved in the problem, and we're trying to eliminate all of the factors of x or the references to x. So we'd have to take another tactic here, and that other tactic is quite simply to expand this expression. So we could write this then as x squared plus 1 squared. Let's square this. We get x to the 4th plus 2x squared plus 1, and then just bring down the dx. Wow, that's neat. Just by expanding, this becomes a rather easy integration problem. We're taking the integral of this and this and this all separately, you see, so it turns out to be, let's see, this is x to the 5th over 5 plus 2 times x cubed over 3 plus 1x, then plus a constant. And that's all there is to it. Again, we could clean it up a little bit, but I think we could see the cleanup rather easily. The point is, we didn't need to go through this sophisticated idea of substitution or using the general power rule of it or anything like that. All we do is expand what we see, and some very nice things happened. We can use the techniques we've been talking about to calculate definite integrals. Consider this problem. We want to integrate from 0 to 1 this function. And we begin the same way that we did before. That is, we want the integral function here. If we're going to use the fundamental theorem of calculus, then we need to find the integral function for this. So let's see. We're looking to see if this is the derivative of that. No, it's not. We need a 2 factor, so we think of multiplying it in by multiplying 1/2 times 2 in here. The 1/2 we kick to the outside, and the 2 we put inside. Now, I've noticed I've written the 2x over on this side for no particular reason, except that maybe we are more accustomed to seeing it that way, but it really doesn't make any difference. Now we're in the form that we're talking about, so it's this single entity to the 4th power over 4 for the integral function. Now, we want to evaluate that, you see, from the upper limit minus the lower limit. So it is 1/2 times, now it is this in terms of 1, substituting or replacing x with 1, and same expression that we have here, but the x is replaced with 1, then the same expression over here with the x replaced with 0. And I suggest that you be very cautious about that and not try to evaluate as you go along. The tough thing about calculus a lot of times is the algebra within the calculus. That's what hangs a lot of people up. And I've had numerous students that have gone through calculus and tell me that even if I teach them at very early stages in the elementary algebra, intermediate algebra levels, when they get to calculus and come back to me, even if they don't have me for calculus, they say, hey, calculus is easy. It's simple. It's the algebra within calculus that's difficult. And the algebra becomes difficult if the organizational skills are low. So So take the time to write this kind of thing out, and everything becomes rather clear rather quickly. So here we have 1 squared is 1 plus 1, that's 2. This is 2 to the 4th power over 4. 2 to the 4th is 16. 16 over 4, that gives the 4 here. Evaluating this, we get 1/4, and half of all of this business is 15/8. Okay. So that's one way to deal with it. I'd like to show you how to deal with the same problem using the U notation. So here's the same problem. Now I've written the x on the right side here of this factor, and now we can make these substitutions. U is the x squared plus 1. The first thing we do is calculate du. The derivative of this is 2x dx. Okay, so du is 2x dx. Now we look here to see about our substitution. We're substituting for x dx. Here we have 2x dx. So we solve this for x dx. We divide by 2 on both sides. So the x dx is du over 2. Okay, fine. Now we can make the substitution back. However, we have to deal with the limits of integration here. Remember, this is x equals 0, x equals 1. And when we go into the form of u, we need u equals something, u equals something. But it's pretty easy to calculate here. So we need to also calculate what happens to u when x takes on these two values at the limits. So if x takes on the value 0, well, look at this. If x takes on the value 0, you see, then u would be 1. So x equals 0 implies that u is 1. Now the upper limit is 1. So when x is 1, what happens? Well, we have 1 squared plus 1, that's 2. So when x is 1, u is 2. Now we're ready to go into the u form. So now it's the integral from 1 to 2. From 1 to 2, you see, of u cubed times du over 2. The substitutions that we're familiar with to this point. So, well, let's see. We'll snag the 2 out. It becomes 1/2 the integral from 1 to 2 of u cubed du. And the u cubed du, that integration is u to the 4th over 4. And we're evaluating, you see, 1 to 2 here. So it's 1/2 of, and again, it's just a straight substitution. The u is replaced with 2, and then the u is replaced with 1. And now we evaluate, we get 15/8 as we would expect to get. The geometric interpretation of this situation is rather interesting. You know, we interpret definite integration as area under a curve. Well, gee, we're talking about two different areas and two different curves here, because after all, in our original problem, we're talking about the graph of this function, you see, and we're talking about the area between the graph of this function and the x-axis within this interval, the interval from 0 to 1. But here we're talking about the graph of x cubed, excuse me, u cubed. Now, I'll use this version. I'm jumping back and forth here because I'm looking at this too, but it's half of this area that we're talking about here for the evaluation, which is to be equal to that. But you know, we could also look at it like this. It's 1/2 u cubed du. You see, that's another way to look at it. But if we constructed the graph of 1/2 u cubed and evaluated the area that's between that graph and the x-axis and within the interval from 1 to 2, it would have the same area as the area of that other region that we were just discussing. So it's a rather interesting phenomena from the geometric standpoint. Let's go through the situation again. I want to show you another problem in two different ways. Here we have, let's see, the integral from 0 to 2 of this. And let's see, we're thinking, gee, is this the derivative of that? We know that this is the inner function, and no, it's not. It's missing a 2. So again, we have to do this 1/2 times 2 business. So the 1/2 comes to the outside, and we have 2x, and we're expressing this as 4 plus x squared to the 1/3. And it would be fine if you want to write this as x squared plus 4, of course. Okay, so we know then from our previous work that our antiderivative function here is this single entity to the 4/3 power over 4/3, and we're evaluating from, within these limits. So we go through that process 1/2 times. Now, it turns out that this 4/3 in the denominator becomes 3/4 up here, and we could actually snag that 3/4 out. Here's the 3/4. We could actually pull it outside of this bracket if we want to, because it's going to appear in both of the terms involving the replacement of the 2 and the replacement of the 0 here when we go to the evaluation process. So we could actually pull it out here. And I didn't do it in my manipulation here, but I want you to know that that is an option for you. At any rate, to evaluate, I'm writing the 1/2 now times. Now, 3/4 times this with the x replaced with 2 is what this is. And 3/4 times this with the x replaced with 0 is what this is. All right, and then as the smoke clears on this, we find the approximate value of the integral, the area under the curve, to be 3.619. Let's go through the process using the U notation. Now, we have experienced a little bit of convolution here, I think, in using kind of a straightforward method. And the U notation should serve to make the manipulation a little bit easier. And I think it does here, even though we have to go through this jump shift on the limits of integration. Here's how it looks. So here's our problem, and I've written this to the 1/3 power instead of the cube root of this, just for convenience. I can go right into substitution like this. But the substitution is that U is this inner function, this x squared plus 4. The du, we just shift right over here. The du, the derivative of this, is 2x dx. All right, now we notice here that we're substituting for x dx. We solve this for x dx du over 2, then is what this becomes. Now we also have to deal with the limits, so we shift right back over here and we say, gee, when x is 0, u is 4. When x is 2, 2 squared 4, 4 plus 4, 8, u is 8. Okay, we have all of the ingredients, so now we have the integral from 4 to 8 evaluated here. Then it is u to the 1/3, and then the x dx is replaced with the du over 2. And away we go. And notice that we're dealing with much simpler ideas here, and we don't really have to back substitute into the more complicated version. Here's what it looks like. We have the 1/2 coming to the outside. We have the form that we need here for the integral function, so it's u to the 4/3 over 4/3, and we're evaluating here our limits for integration. And then this I'm going to rewrite. I'm going to simplify this in one more step, writing this as 3/4 u to the 4/3. I've done this up here. Okay, so we have 1/2, 3/4 u to the 4/3, and then our limits. So now on this one I have taken the 3/4 out, and just to show you the simplification of that, and it makes things really clean right in this part of the problem. So the 3/4 comes out and I have 3/8, and then u to the 4/3, replacing u with 8, I have 8 to the 4/3 minus 4 to the 4/3. A really clean form here, and then I've simplified a little bit in this step, but even from right here, we could just pop this into the calculator and make our approximation accordingly. But it turns out to be exactly as it was before, as we would certainly expect. Let's take a look at the graphs of the two functions on the calculator. Here's our first function, and notice it's entered in the way that it appeared on the board, x squared plus 4 raised to the 1/3 power times x. And the graph. And we're going to look at the integral from 0 to 2 in just a moment. We want to integrate from 0 to 2 on this particular graph. And remember, we're integrating from 4 to 8 on the other one. Let's go ahead and enter the other graph, though, and we'll perform the two integrations at the same time. The other function was u to the 1/3 times du over 2. The du over 2 means 1/2 du. So I'll enter the 1/2 as 0.5. Now I want u to the 1/3. I don't have a u available. I'm going to use x to the 1/3. Here's the 1/3 and the graph. Now the graphs, as you can see, look quite a bit different. And you wouldn't suspect that we would get the same integration, definite integration, over the two different intervals, but we do indeed. Let me make the calculation here. I'm pressing second and trace for calculate. I want item number 7, and you notice here that I'm on the first equation, or the first graph, and so I want the lower limit. Let me cursor over to 0. We're integrating from 0 to 2 on this one. So I'm sliding over. Here comes the icon. There we are at 0. Enter. Cursoring to the right. Boogieing over to 2. Enter. And we get a nice, nice shaded region, and we have the number associated with the area under the curve, 3.6188984. Okay, let's go to the other one now. We're performing the same calculation, so it's second and then calc, and item number 7 again. And now I want lower limit, and I notice that I'm on the first equation. I need to jump to the second one, so I'm cursoring down, and I jump onto the second equation, so I boogie on over to 4. Enter, and then I'm sliding over to 8 for the upper limit. Here we are. And the number is exactly the same as the number we had before, as we would expect. But it's rather interesting that we have two entirely different graphs and two entirely different looking shaded regions here, and yet the integral is exactly the same. Even with all of the processes we've learned up to this point, integration can be rather cumbersome, and any little advantage that we can realize along the way will be helpful. Here's a little bit of an advantage that we can utilize involving even and odd functions. An even function, recall, is a function which is symmetric about the y-axis. Now, graphically, that's the interpretation. Algebraically, even functions have the characteristic that f of x is equal to f of negative x. Here's the graph of an even function. All right, now, consider that we're taking the integral from negative a to a. Now, notice we are integrating sort of symmetrically about the y-axis, and we have a graph that's symmetric about the y-axis. Interesting little set of circumstances here. So, but if we're taking that integral from negative a to a, we might notice that the area over here and the area over here are identical, and so to realize a little bit of efficiency in the calculation, we can just say that this area is 2 times that area, you see. Or the integral from negative a to a of f of x dx is 2 times the integral from 0 to a f of x dx. Perhaps not a great deal of gained efficiency here, but a little bit. The situation with odd functions is even nicer. Odd functions now, remember that graphically, they are symmetric about the origin. And when we talked about this earlier, we talked about a kind of a double fold, kind of a, they have the characteristic that if you fold here and then fold here, fold along both axes, it'll fold onto itself in a fashion. And algebraically, it is that f of negative x is equal to the negative of f of x. And so we can evaluate whether or not we have an odd function by going through this process. At any rate, here's the graph of an odd function. And if we're talking again about taking the integral symmetrically about the y-axis, that is the same distance on both sides, then some rather nice things happen. When we look at an area that falls below the x-axis, remember we can consider it to be negative, and an area above is considered to be positive. So we have a negative area here, a positive area here, and they negate one another. So the integral from negative a to a of an odd function f of x is simply 0. Now, this efficiency manifests itself in a problem such as this. Suppose we want the integral from negative 4 to 4 of this polynomial function. Now, the integration is relatively easy here, but yet there is some considerable manipulation involved to figure it out. It's not difficult, it's just a little cumbersome. And we can simplify matters very quickly here by identifying sort of an even function, odd function situation involved here. Suppose I separate this polynomial into x cubed minus 2x and consider that I want the integral of this dx and then plus, and I'll take the other parts, the 6x squared minus 3 parts, you see, and I'm separating into even and odd. So this is the odd function part, and I can identify this as the odd function part if I go through the process of testing whether or not f of negative x is equal to the negative of f of x. I could do that. But at any rate, it turns out that this is an odd function, and so I have this symmetric integration kind of idea here, and the area involved here would be 0. So this completely goes out, and I don't have to deal with that any longer. And over here, some nice things happen as well. This turns out to be even, and therefore it's double the integral from 0 to 4, same function dx. All right, now, when I integrate, now you notice that this is pretty easy to find the integral function. It's 6 times x cubed over 3 minus 3x. Okay, and these are my limits. And when I pop in, now I went ahead with a cancellation here and burned another step, but when I pop in these values for upper limit, lower limit, notice what happens with the lower limit. I put a 0 in place of these x's and this goes out. So all I have to do is evaluate at the upper limit and double that amount. No big deal. I replace these x's with 4's and then evaluate. It turns out that the integral is 232, and we gain some efficiency by realizing or by utilizing these ideas of even and odd functions.